Hi, so welcome back. In this lecture, we will learn about averages. Okay, that's the more colloquial word that is used, but the more mathematical or a fancy word to use for averages is expectation, and that's what we are going to stick to for the rest of this course. Expectations. Okay, and we have already introduced what an expectation is. In the assignment that we had solved the last time. So expectation was, we had discussed it for the discrete case. I will discuss it for the continuous case as well, but really the two cases are analogous. And so discussing one of them is just, is good enough. The other case can be extended. So what we are going to do is to discuss mainly in the setting of discrete random variables. We are going to discuss expectation in that setting, and the continuous case is just going to be, conceptualized from the analogies that we can draw. Okay, with the discrete case. So let's just go over the formulas first. Expectation of a random variable x. Okay, will be given by two formulas according as whether x is discrete or continuous. If x is discrete, this is the one that we have already seen in the assignment. It's the summation. First of all, the summation has to be over all the spectral points. And the terms of the summation will be the xi's of the spectral points multiplied by the PMF of the discrete random variable, the probability mass functions at each spectral point. Okay, and for the continuous case, as we know now very well that summations are replaced by integrations. Here, the integration has to be over all of real numbers from minus infinity to plus infinity. Here, it was the summation was over the spectral points because the PMFs were defined only at the spectral points. And here the integration is from over all of real numbers is because the PDF is defined over all real numbers. Okay, so probability mass functions are replaced by probability density functions, as is always the case when you go from discrete to the continuous case. So summation replaced by integration, probability mass function replaced by probability density function, and xi's, which were discrete points, and that's why this I was the listing or was numbering, indexing the spectral points. These xi's are replaced by just a continuous x. Okay, and that's what it is. That's the formula for expectation for the discrete case and the continuous case. The two are really the same, except that you have to make the adjustments, the usual adjustments that you need to make when you go from the discrete case to the continuous case. Okay, that's the formula. It has some properties. We will go over the properties in somewhat detail, but let's first give. So as I've already mentioned that the discrete case and the continuous case are really analogous to each other. You just have to make the usual adjustments. So I think it's enough to just understand expectation in the setting of a discrete random variable itself. Okay, if we discuss the properties and how it looks, what it is, all the nitty-gritties of the expectation in the discrete case, we have more or less covered the continuous case as well, because you just have to make, as I said, the usual adjustments and things will be exactly the same. Okay, so we will discuss this in the discrete setting. Yeah, okay, so let's just give an example. So I think we will stick to this one, this formula for the discussion, and I'll just rub out the others because we're going to discuss this for the moment, and that would be enough. So this is really the expectation when x is discrete. Okay, x here is a discrete random variable. Now, the example would be suppose there is a class of say 6 students. Okay, this is student 1, student 2, 3, 4, 5, and 6. There's a class of 6 students, and they just had an exam, and you want to find the average marks in that exam for this class. Okay, one way to find that out is to define a random variable. Okay, so this is really the sample space. Let me call that S, because if you think of this as an experiment, these are the outcomes. In this class, you have only 6 outcomes. That is, those are the 6 students. That's the universal set or the sample space, and we want to find the average. The objective is to find the average of the marks. So I think the best way we can define a random variable is to define it from S to the real numbers by whatever marks each student gets. For example, if the first student, S1, gets 70, let me just write 70. In other words, this is the value of X at S1. Okay, X takes S1 to the marks that S1 gets, that is 70. Okay. Similarly, let's just say that S2 gets a 70 as well. So that would be X S2, S3, S4, and S5. Let's say that they all get 80 each. Okay. So it's not alpha. It's X S3, X S4. X S5, and finally the student 6 is a good student, is probably the best student, gets a 90, and that's your X S6. So that's the random variable. I've just defined, this is what I'm interested in, the marks. Okay, so I've defined the random variable with the purpose that if I want to find the average marks, I want to define the random variable with whatever, assign each student with the marks, the mark that the student gets. Okay, all right. And now, if I want to find the average, really forget what this formula is. I think the simple formula for if I want to find the average, I think what we know is that we add up all the marks and then we divide by the total number of students there are. So if we add up all the marks, we get a 70 plus a 70. There are 3 80s, and then there is a 90, and this is divided by 6. Okay, that is the average, whatever it comes to. Okay. Now, one way that we can sort of give it a more general formula is to think of 70 is to basically assign weights to each of the marks. Okay, so 70 happens twice in the summation, so it gets and the whole thing is divided by 6, so it gets a weight of 2 by 6. Okay, let's just rub out these properties for the moment. Okay, we will come to them as we need them. So 70 gets a weight of 2 over 6. Okay. 80 gets a weight of 3 over 6. Okay. And 90 gets a weight of 1 over 6. Okay. That's quite evident because you really have 6 dividing each of them, and you're adding the total number of times these numbers happen. That gives each number, each mark, its weight. Okay. Well, and then if you sort of so what we can do is this 70 is, if you look at it, this 70 here, it actually comes from S1 and S2, and you can think of this. Okay, so if I for this particular sample space or this particular random variable, if I write down the spectrum, of X, what's the spectrum of X here? These are the values that X can take. What are the values that x is taking? It's taking the value 70, it's taking 80, and it's taking 90. Okay, so this is really the image set of x in the real number set. Okay, so that's just 70, 80, and 90. So if I want, I can call this x1, I can call this x2, and I can call this x3. Okay, so really this is 70 is just x1. So let me just replace that by x1, and 2 over 6 is the probability that x takes x1, that is x takes 70. X takes 70 when the event is s1 and s2. Okay, I hope that's clear. X takes x1 is basically the same as saying that the probability of you pick these two students, s1 and s2. This is the event from the sample space. Okay, and that is, how many are there? There are 2 out of the 6, so that's 2 over 6. Similarly, 80 would be x2, and 3 over 6 is the probability that x takes x2. I think that's, again, quite clear. X takes x2, the value x2 is the same as these 3 put together as one event, and that has the probability 3 over 6. And similarly for this one, x3, probability x takes x3. And that exactly matches with this. You can see the sum, it's a sum of these terms, xi multiplied by the PMF at xi, okay, and the summation happens over all the spectral points. These are x1, x2, x3 are all the spectral points, and therefore that's the formula, okay, and that's the motivation for defining expectation like that, and it makes sense because it matches with our normal sense of what an average is, okay. If you want, you can look at it slightly differently as well. I mean, it's the same thing, but what if I did not give them weights like these? What if I kept... so I can also take average, like, so I'm starting from this step and I'm writing it here. So what if I did not collect the 2 70s here and the 3 80s here, but kept them as they are? So then the first 70 would get a weight of 1 over 6. The second 70 would get a weight of 1 over 6. This first 80, all the 80s would get a weight of 1 over 6. And the 90 would get a weight of 1 over 6, right? I've just kept them, this is the same thing, writing these two to get in as a summation, and this one is the same thing, okay? But I'm just saying that you could, if you wanted, you could have done the problem or found out the average by this way as well. You know, find out this term, find out this term, all the terms, 6 terms, and then add them. That's enough. It would match with this answer. Now, what about this? I mean, this basically corresponds to the 70 from S1, okay? So let me just write, this is the 70, which is XS1, okay? The value of X at S1, that's 70. And this is really, what is 1 over 6 is the probability that you would pick the first student out of the 6 students, okay? So, this 1 over 6 is really the probability that you have S1. That you pick the student, this event, a singleton set, okay? This 70 is the value of the random variable at the second student, S2, and the probability that you would pick the second student, okay? And this way you can just continue, okay, till the last one where 90 would be X, the value of X at the student 6, and the probability that you would pick the 6th student. This is another way of looking at it. And then this would be the summation of x SIs, okay, SIs are all the outcomes, the probability of each singleton set out event, and these SIs, they are all the outcomes. In other words, they belong to the sample space. This is another formula. You can this formula is the same as this formula. So expectation can be expressed as this formula, or if you this is summing over the spectral points x1, x2, x3. Okay, and this is summing over all the sample space points or the outcomes. Okay, they are the same. In this sum, you have 70 twice with a weight of 1 over 6. That's the same as 70 with a weight of 2 over 6. Okay, and that's why if you think about it, this P x equals x1 is really collecting these two together. Okay, and here they are separated, 1 over 6 and 1 over 6, they're separated. Okay, this has 1 over 6 and this gets a 1 over 6 as the probability. Okay, and that's why these are called PMFs for a reason. They act like mass. This is the probability mass function because they are acting like a mass. So you can think of the mass of S1 as 1 over 6 and the mass of S2 as 1 over 6. When you write it like this, it's like, sort of clinging them together, putting them in one box, and the mass of this two together would be the mass of the first one and the mass of the second one, which is 2 over 6. Okay, so therefore the mass of this collective unit with S1 and S2 in it is a 2 over 6, and the individual masses were 1 over 6 and 1 over 6. That's why it's a mass function. Similarly for this one, probability x equals x2, really x equals 80 means that you're looking at these three together, that gets a mass of 3 over 6, but individually they all had a mass of 1 over 6. It's like that, okay? That's why it's called a probability mass function. Anyway, so we can, so what we have is, we have two formulas for expectation. This is the first formula and this is the second formula. They are the same, except that we are summing over different things, different sets. Okay, and we can use them whenever, in whichever way we like. Okay, right now that's all about, that's what we needed to learn about the basics of averages or expectation. Let's now go over a few properties that I had listed out here, but I have obviously rubbed them out because there's a lack of space here. So let's just write out the properties once more, and I think the first property that is very important, so properties of expectation, obviously, is going to be what is called the linearity property. The linearity property, where there are two parts to this. The first part would be that if there are two random variables, x and y, and if you add them and form this new random variable, then, so in other words, you're taking the average of this new random variable, then that's the same as taking the individual averages and adding them. I think that makes sense intuitionally also. And if you have a new random variable from an old random variable x by multiplying it by some constant c, that's the same as first finding out the average of the random variable and multiplying that by c. Okay, so yeah, I mean, I think these two make very good sense from the point of view of intuition as well. I mean, if you have an average and if you multiply the numbers themselves by a constant, then the average will be multiplied by the constant itself. I think that's perfectly all right. The second property would be, and this happens all the time. In other words, it doesn't matter whether x and y are independent, they are dependent. So I've not given any condition here. So this condition holds even if x and y are dependent on each other. Okay, so that's a very strong property to have then. Okay, so in other words, x and y don't have to be very separate from each other. They can be sort of they can have some connection between them, and still this property would hold. The second property is is when if you take the product. I'll just write product. Okay, this is if you take the product of two random variables, then that would be and if you find the expectation, that would be the product of the individual expectations. But over here, we need the condition that x and y will have to be independent. Okay, right. So let's go over the first one first. Okay, I think to prove this one will be very easy. But to prove this one, we will make use of the second expectation formula that we have used. That comes in. That's a better way of doing it. So if you remember what that was just summing over the sample space. So SI's were from the sample space, the values of the random variable at each outcome multiplied by the probability that you would get that outcome. Okay, that was the formula. And now if you just replace this by x and y, in other words, if you have two random variables, and if you're taking the summation of these two, think of this as a new random variable. If you want, you can call it t. Okay, so that's just the same as taking x, the summation over all the samples space points, in other words, outcomes. Instead of x, you now have t of si, and the probability that you take that you get each outcome. Of course, t of si is the same as, or let me just write it out. So it's the same as x plus y on si. In other words, the value of this t is just x plus y. Probability si. But of course, the way addition of functions is defined is this really is taking the value of the first function at si and taking the value of the second function in si and adding them. So really what this is just the value of x at si added to the value of y at si. Okay, and let's just put them together in a bracket because we're multiplying this whole thing by this thing. And this, of course, is the same thing, the summation space here. Okay, all right. Now I think it's very clear. You can just separate the two summations. So here I get x at si, probability at si, plus the summation y at si, and the probability of si. Okay, of course, the summation points will remain the same. I've just separated the two sums, and by this formula, you can see this is the expectation of x, and that would be just the expectation of y. Okay, I've just replaced x by y here. Okay, all right. So that is plain and simple. This one is also very, very simple. If you just multiply by c here, in other words, this is the new variable. This is the new random variable, which is this random variable. Okay, this is the old random variable multiplied by c. But of course, what that means is, it means that you're first finding the value of the random variable at xi, and this is a real number, so multiply that by the constant c. That's what it means. Okay, probability this si in s. And this c is a constant, doesn't do anything to the sum, so you can just take that out. You can just take that out over here. And this is just the old formula for average. So c times expectation of x. I think that's very clear. Okay. All right. So that's about the first property, the linearity property, and you know, just notice here that while doing this, we did not have to assume anywhere that x and y will have to be independent. Okay. It just follows. Okay, from the formulas themselves. Okay. All right. We'll do the second one. For this one, we need independence for this one. Okay. And that's also quite easy if we assume that condition. So expectation of this product will be, for this one, I will use the first formula of expectation that I had used, which is, I ran out of space with my previous recording. So let's just continue what we were doing. We were proving this second property where the expectation of a product of two variables was equal to the product of the individual expectations. This is when x and y were independent. And this was and I said that we would use the first formula for expectation to prove this particular property. So this is the first formula that we had given for expectation, and this is what we are going to do. So really, so let's just write that out in terms of xy, this product xy, which we can call t. So expectation of this new variable, random variable, the product, which I'm calling t for simplicity, is going to be the summation over the spectral points of xy now. Okay. This was for expectation of x, we had to sum over the spectral points of x, but this is now xy, so we have to sum over the spectral points of xy, this variable t. Okay. And what can be the spectral points of xy? Well, x can take xi's as values, y can take yj's as values. So xy will take the values xi, yj. And we will establish that by an example. We were doing an example already. So, and so if these are the spectral points, let's just believe for now that these are the spectral points, then by the formula, you would have the spectral points multiplying the probability mass function of this new variable xy, which is t. Okay. So why? Let's just discuss this xi yj thing here. I want to find out what would be the spectral points of xy. What will be the spectral points of xy? So for that, we will take another random variable. So in the previous case, we took this class of 6 students. We call that the entire thing was a sample space S, and X was a random variable which was measuring marks. So the first 2 students got 70, then the next 3 got 80, and the last one got 90. So the spectral points of X were 70, 80, and 90. We call that X1, X2, and X3. Let's define another random variable where we want to look at the attendance of each of the 6 students. Okay, so the first student gets a 60% attendance. The next two, 70%. The fourth one gets an 80% attendance, and the last two get a 90% attendance. So the spectrum of Y here is going to be 60, 70 twice here. So 70, 80, and 90 over here. So there are 4 spectral points of Y. Okay, so what would be the spectral points of X? So these spectral points of Y, spectral points of X. So if I want to find out the spectral points of X, Y, what would that be? Well, that would be x, y acting on each of the sample space points or the outcomes. So xy on S1, xy on S2, like that, xy on S6. Okay, so this will be the spectral points. As is the case, the spectrum of y this really was y of S1. This, for example, was y of S4. Okay, this was, S5. This was y of S6. Okay, so if you take them as a set, okay, So 90 here comes from y of S5 and y of S6. Of course, I've written it only once because they are both 90. Y of S5 and y of S6 are both 90. So the spectrum of any random variable is just the action of, it's the image set. It's the image set of xy now on, so this is, so xy, so let's write it here. xy, of course, is also acting from S to R, and it's taking any Si and giving it this value xy si, which really is the way products of functions is defined, is x on Si and then y on Si. Okay, so this is, so you collect all these numbers and that will be the image set of xy, which will be the spectrum. So the first is the action of this function on S1, which really is the action of x on S1 and the action of y on S1 multiplied together. So this will be what? X on S1 is 70. Okay. I'm going to give them the general names x1, x2, x3. So let's, I mean, if just for clarity, let's just write that once more. This product means x on S1, y on S1 multiplied together. This means x on S2, y on S2 multiplied together. And this means that x on S6, y on S6 multiplied together. Okay, so let's just write that out. So x on S1, this is x on S1 is 70, which is x1. Okay, and y on S1 is 60, which is y1. Okay. Okay, x on S2 is 70, which is again x1. And y on S2 is 70, which is y2. Okay. What's the next one? It's x on S3. X on S3 is 80, which is x2. So x2. And y on S3 is 70, which is y2. What's x on S4? So let's just complete it. Okay. So that you will. So we have 3 till now. We have to find on each of the S6 students. Okay. Each of the 6 students. Okay. So the next one is going to be y on this one S1, S2, S3. Y on S3. Y on S4 is 80. That is x2. This is x on S2. X on S4. All right. This is x. So this comes from the first student. This comes from the second. This is a product of the marks and attendance for the first student, product and attendance of the second student, the third student, for the fourth student. So x on S4 is 80, which is x2. Y on S4 is 80, which is y3. This is for the fourth student. For the fifth student, x on S5 is 80, which is x2. And x and y on S5 is 90, which is y4. Y4. And for the last student, it's going to be x on S6, which is 90, that is x3. And y on S6, which is 90, that is S4, y4. So really, I can just rub them out now. Or let's just, yeah. This is the spectrum. You can see the spectrum of xy is the action of xy on each of the students is given by, well, whatever x runs on. X, if you look at this, x runs on x1, x2, and x3. This up to x3 here. Y1 runs on, or y runs over y1 through y4. So y runs over y1, y2, y2 here, y3 here, and y4 here. Okay. So really, it's going to be mixed. That's why I've given xi, yj, because for these two, for example, you have x1, but you can't call this one by the same index. You can't call this xi, yi, because the index of y is changing from y1 to y2. over these two. Okay, but the index of x remains the same. They're both 1. Okay, so really you have to, so things can play out in whichever way this product will pan out. Okay, all right. So spectrum of xy will look something like this: xi, yj. All right. But so what can we do with this now? The way to look at it is, so I'm going to repeat this here. Okay, I'm just giving a this space mark over here just to say that this is the same the summing space that is going to be written here. So xi yj. What about this? This probability that this random variable is equal to xi yj is possible when the capital X, the first random variable, marks takes xi and attendance takes yj. So that's the same as writing probability that marks takes xi and attendance, the second random variable, takes yj. Okay. Well, this really is an intersection of two events. It means that this event is x equals xi, this event is y equals yj. So both will happen. This and this will happen. Then only the product of xy will be xi yj. Okay? And so, the way you can write this is, you can actually now bring in conditional probability. You can condition this with, let's just fix y equals yj, and x will be equal to xi with the condition that y equals yj, but then we have to multiply by probability that y is equal to yj. Okay, so think of this as event A and event B. A intersection B is A conditioned by B, and then multiplied by probability of B. Okay, that's what it was. And now, of course, we have to use this. X and Y are independent. Because x and y are independent, the fact that x will be xi will be independent of whether y is equal to yj or something else. So this will be, it does not, so the probability of x equals xi does not care about this conditioning. So they're independent. So this is just going to be probability x equals xi. It will not bring in it will not continue with this conditioning because it's independent of it. And this one will remain what it is. Okay. Now, the important thing to note here is this, that so far, now what I can do here is, instead of writing, so I said that I left a blank here just because I wanted to copy this xi yj in spectrum of xy. But instead what I'm going to write is that xi in the spectrum of x and yj in the spectrum of y. Okay? I hope this is clear enough, okay? What I'm writing, I hope, so really what I'm doing is I'm taking this sum here, okay? This, instead of just bluntly copying this, I'm changing this summation space a little bit. I'm saying that xi will range over spectrum of x and yj will range over spectrum of y. The question is, if I change this summation space here, will the two sums come out to be the same? That's a question I have to answer, or that's a question whose answer should be yes, only then can I replace this by this summation space, okay? The answer is yes, really it is yes, because, for example, so this means that xi will take all values in its spectrum, and yj will take all values in its spectrum, in the spectrum of y. So, in other words, a value like x2 y4 is permitted. X can range over x1, x2, x3. Y can range over y1, y2, y3, y4. So x1 can be x2 and yj can be y4. Okay, that's permitted if I consider this, summation space. But then this is not in the spectrum. This x2y4 is there. So let's take something else. x2y1 is not there. x2y1 is not there. Okay, x2y1 is not there. So let's take x2 as I as 2 and j as 1. This is there. This is allowed now. Sum over this is allowed in here, but x2y1 is not in the spectrums, right? So there is a problem. So if I change the summation space from here to here, this one to this one, a point like this is allowed here, but a point like this is not allowed here because this x2y1 is not in the spectrum, right? So what's happening? But the thing is, this x2y1 means that the probability will have to be x2 and the probability that x will be x2 and y will be y1. Okay? But that probability is 0 because x2 and y1 never happen together. You see that. Okay? There is no x2 and y1 together. So immediately, that just because we have this probability of x will have to be x2 and y will have to be y1 together, that probability will become 0 because the fact that x will be x2 and y will be y1 is a null event. And so that probability is 0. So even if this point, which is not there, even if this is included in this summation space, the contribution of the sum for this point is 0 because the probability will make for this point will be 0. Okay? So really, whichever points are not included in this, even if they're included here, because the probability of those points will be 0, the two sums will come out to be the same. In other words, only those sums, those contributions or those non-zero terms will remain which are allowed by this spectrum. Okay? So really, you can change this summation space to this summation space, and then there is no problem. We can continue with this summation space. Okay, so finally we have this xi from the spectrum of x and yj from the spectrum of y, and now this is just regular. Okay, so this now means that I can sum over two. I can just separate the sums. I can take up a strategy. I will, this is from spectrum of x. Let's say I will first sum over the spectrum of y, and then I will sum over the spectrum of j. So if I sum over the spectrum of y, I have xi, yj, probability x equals xi, probability y equals yj. Because over this sum, the xi's and probability x equals xi, these have no value. These are really constants. The summation is happening over these numbers. They are constant. So this will just be probability or summation xi equals spectrum of x. You can just take them out. Okay. So this is just going to be xi, probability x equals xi. And the summation will happen only over yj. Okay, it's just going to be yj, probability y equals yj. But then this is the expectation of y, right? This is the expectation of y. So I can so let me get rid of this example now. I don't need it. This is just to establish what was going on in the summation part here. So this really is just going to be, so this is the expectation of y. So it's just going to be a summation that xi, the xi's vary over the spectrum of x. Xi probability, x takes xi, and this is just expectation of y. Okay, so that is expectation of y, which is a constant, which is the average of y. That's a constant number, so I can really just take that out. Okay, so I can write it outside. It's expectation of y. And then once this is taken out, you have a sum of xi, PMF of xi, and that's the expectation of x. So you're just going to get expectation of x and expectation of y product together, and that's your result. Okay, so two important things, two important results. These are very important. These two properties are used all the time. Okay, and they're important to remember. The first one had no such condition, but this one had this condition, and it's important that you can sort of break this product up in their own expectations only if they are independent. Okay, all right. With that, I think we will just do one or two examples of how to actually find expectations for a couple of random variables, standard random variables that we have already learned. We have already found in the assignment, we found if x was a binomial distribution with random variable n and p, we had already shown that the expectation of this random variable was np. Okay, this was one of the problems in the assignment, and we had also worked it out when we were working out the solutions for the problems there. And this we already know. Okay, what about, so let's say I have another variable y, or I'm just going to call it x. So I have a variable which is not binomial. So let me just write binomial here for binomial. Okay, what if I have a random variable which is a Bernoulli trial with a parameter p, that is the probability of a success? What would be the expectation of a random variable with a Bernoulli distribution like this? Okay, what would that be? Well, let's just use the formula. It's going to be, so what are for a Bernoulli trial, the spectrum of x, what is the spectrum of x? Just two values, success and failure. In other words, 0 and 1. Okay, that's it. And what were the probability mass functions? Probability that x will be 0, that you will have, or let's say 1, probability that you will have a success, x equals 1 is a success, was with probability p, the small p, the parameter, and the probability that x will be a failure will be 1 minus p, which we sometimes called q. Okay, and that's the PMFs. So this is just the two spectral points. So let's just sum over the spectral points. The first spectral point is this one, 0. So the first point is 0 multiplied by its PMF. And the second point is 1 multiplied by its PMF, x equals 1. And that's just 0, it gives me 0. This whole thing is 0. And that's just 1 with, this is p. X equals 1, probability x equals 1 is p. And so the expectation of x of a Bernoulli trial is just the parameter itself, p. Okay, and that sort of makes sense. I mean, intuitionally also, you can think of heads tails as a Bernoulli trial. Okay, success and failure. What's the probability of if you do it, if you flip a coin many times? What's the probability? What's the average that you would get if you sum all the numbers, the zeros and the ones? It's half. You can expect out of 100 times, around half the time you would have 1, and around half the time you would have 0. So if you added all the numbers and divided by 100, you would get around 50 by 100, which is half, which is really the parameter, right? And heads, tails, this Bernoulli trial would have a parameter half because heads happens with, or success happens with a parameter or with the probability half. Okay, so that matches with our intuition also. And I think what this does is you can the way we had found the expectation for the binomial distribution, the random variable with the binomial distribution, was by using this formula as was given in the assignment. But now we have a very important tool. We have the linearity property for this expectation. Okay. So, for example, if y is a binomial distribution, let's just write y here. Okay. I want to keep x for Bernoulli. Okay. If y is a binomial distribution with np, then we know that y could actually be expressed as a summation of n Bernoulli trials, which are IIDs. Okay, so each xi is a Bernoulli trial with probability p, and they are IIDs. In other words, independent and identically distributed. They're all distributed like Bernoulli p. And so, if you want to find the expectation of y, which is the binomial distribution, is just the expectation of x1, x2, up to xn. And by linearity, you can just add all the individual expectations. Expectation of x1, x2, up to expectation of xn. And because these are all Bernoulli trials with parameter p, we just found out the expectation of a Bernoulli trial. It's p. So you have p n times. Okay? And that's just np. And that's immediate. What we found by that entire process of using the actual formula for expectation. But now with this very important property of linearity, once we know the expectation of a Bernoulli trial, we know the expectation of a binomial, because binomial is really a combination of n Bernoulli trials. It's a summation of n Bernoulli trials. That's it. Okay. We'll do one more. We'll do the let's say Z is a Bernoulli is a Poisson distribution with parameter lambda. Okay. Z normally is used for normal distribution, but I'm just going to use this other variable here because we are using X for Bernoulli, Y for binomial, and let's use Z for Poisson distribution. Poisson with parameter lambda. Let's just do this. What about the expectation of a Poisson distribution? The expectation of a Poisson distribution by formula would be just sum over all the spectral points. Now, if you remember the spectrum of a Poisson distribution, the spectrum of Z would be all points, all non-negative integers, okay, up to infinity, starting from 0. So I will have k's starting from 0 to infinity, k. So these are the spectral points. The first point is, k is 1, 0, 1, 2, the spectral points, x1, x2, x3, like that. So k with probability x equals k. Well, let's just work that out. This is just going to be, actually the first point, when k takes the value 0, the first term is 0. So you might as well start from 1 to infinity, k. Let's just write the probability mass function for Poisson distribution. That's e to the power minus lambda, lambda to the k over k factorial. Sorry, k factorial. Well, the k and the k from this k factorial will cancel. So you will be left with, I'll just write it once more. You will be left with e to the minus lambda, lambda to the k, k minus 1 factorial. Okay, and then what we can do is, because now we are starting from, let's just do this. So this e to the minus lambda has nothing to do with this summation. So that's a constant. So let's just take that out. E to the minus lambda is out. I have k from 1 to infinity, lambda to the k, k minus 1 factorial. Now, I want, because there's a k minus 1 here, I want to get a k minus 1 over there. So if I get a k minus 1 over there, I need to multiply a lambda here, but that lambda would be constant with respect to the sum, so I'll just take that out. I have this lambda outside. So now I have the same thing. So let me just use r for k minus 1. So this will just become, so lambda e to the minus lambda. I have summation. This is going to be lambda to the r, because k minus 1 is r, and you have r factorial. Now, what about if this was k from 1 to infinity, I want to change that to r. If k starts from 1, so this is minus. If k starts from 1 to infinity, r is 1 less than k, r will go from 0 to infinity, because infinity minus 1 is just infinity, okay? And that's the formula for exponential of lambda, okay? I hope all of you can identify that. This is just the summation, the expansion by Taylor series of, exponential of lambda. And this e to the lambda and e to the minus lambda will cancel, and you will have lambda, okay? That was, so the expectation of a Poisson distribution with lambda as its parameter will be lambda. That's just from the formula itself. However, if you want to be a little bit smart as well, we said that binomial NP starts to behave like Poisson lambda if n becomes very large and p becomes very small, such that NP remains lambda, or NP remains as a constant, okay? This remains as a moderate number, okay? Well, because NP was the expectation for a binomial distribution, and we called it lambda, okay? Therefore, just taking the expectation would therefore would mean that lambda is really, for this Poisson, from what we have found here, lambda is really this NP. In other words, lambda is really the expectation of the binomial distribution, which has a very large n and a very small p. And so, it doesn't matter how much big you make n or how much small you make p, the distribution will keep because it's a binomial distribution, it will keep its expectation intact, right? Because even though n is big and p is small, but the formula for its expectation remains np. So even though binomial starts to behave like Poisson in these conditions, and because lambda is actually the np, so lambda will remain as, so np, which is moving under this condition, this is the expectation of binomial, which will, so what I'm saying is this is the expectation of the binomial distribution, which is y, which will then carry forward as the expectation of the Poisson distribution, okay? So binomial becomes Poisson under this condition. So the expectation of binomial becomes the expectation of Poisson, okay? And that's what this said. The expectation, when binomial starts to behave like Poisson, the expectation of binomial will start to behave like the expectation of Poisson. And that's what it says, okay? All right, I think we will finish this here. And we've just worked out a couple of problems just to show how we can put this to use, how to find expectations of different variables, random variables. And as I said, the case for the continuous random variable is just analogous to this case when x is discrete, and when we take up distribution continuous random variables, okay. Wherever we need expectation, in those cases we will just do the problems or develop the theory drawing analogies to what we have studied in this lecture. Okay. All right. So we will finish this here. Take this forward in the next lecture. Thank you.